In the last video, we learned how to classify critical values as either a local maximum or a local minimum, two different ways, using what's referred to as the first derivative test and using what's called the second derivative test. That's the topic for this section, and that's what I want to show examples of in this video. The first example is this polynomial, f of x equals 2x cubed minus 9x squared minus 24x plus 5. What I'm going to try to figure out is where the function has a local minimum and where it has a local maximum, and what the value of that maximum is and what the value of that minimum is. And note that this time I'm using the word relative instead of the word local, even though those mean the exact same thing, just because sometimes these words are used instead. So you're looking for a local maximum and a local minimum. How do you do that? You first need to find your critical values. Critical values are points at which the first derivative equals 0 or is undefined. So I got to figure out the first derivative, f prime of x. The first derivative of this function is 6x squared minus 18x minus 24. This function, like most of the examples we'll see in our class, is never undefined. So really, to find critical values, I just want to figure out when this thing equals 0. When does 0 equal 6x squared minus 18x minus 24? I think we solved this exact thing in a previous video. We recognize that all three of these terms are divisible by 6. So if I divide both sides of the equation by 6, I get 0 equals x squared minus 3x minus 4. The nice thing about x squared minus 3x minus 4 is it factors. It factors to x minus 4 times x plus 1. So I get solutions to this equation anytime x minus 4 equals 0 and anytime x plus 1 equals 0. Anytime x is equal to 4 or x is equal to negative 1, my first derivative is equal to 0. In other words, I have a critical value. The first step to finding my local or relative maximum and local or relative minimum is to find my critical values. My second step is to classify those critical values. I have two different ways to classify critical values. I can either use the first derivative test or the second derivative test. I'm going to try to use the second derivative test, knowing that if it fails me, I have the first derivative test to fall back on. To use the second derivative test, well, you need to know what the second derivative is. Fortunately, the second derivative is really easy to figure out because the first derivative is just a polynomial. So I take the derivative of this derivative and get 12x minus 18. To classify my critical value at 4, I evaluate f double prime of 4. That's 12 times 4 minus 18. That's 48 minus 18. That's 30. Although really I don't even care about this value, the important realization is that that's greater than 0. Think about what that means. Even if you don't have the graph, you can picture the behavior at x equals 4. You know that the graph is flat at that point, and you know that the graph is concave up. Here's what a graph that's concave up looks like, and here's the point at which a concave up graph is flat. This sure looks like a local minimum to me. What that means is that at this critical value 4, I have a local minimum. So this question about finding the local minimum happens at x equals 4. But that's just one of my critical values. I also had a critical value at negative 1. But it's easy enough to classify that critical value. Just evaluate the second derivative at negative 1. 12 times negative 1 minus 18 is negative 12 minus 18, or negative 30. Again, I don't care about the value. I just care that this thing is less than 0. What that means is my graph is concave down. I already knew that my graph was flat because it had a critical value, and the point at which a concave down graph is flat is a local maximum. The critical value at negative 1 is my local or relative maximum. Note that in this case, we added on this extra point. Often we're not just interested in where the local maximum and local minimum are, but what the value of the function is at that point. At this point right here, negative 1, I have a local maximum. But how high is it? Well, I don't know. At some point that's a little bit less than 20. And at this point down here, x equals 4, I have a local minima. But how low is it? I don't know. It's like negative 108 or so. I can't tell. Fortunately, there's an easy way to figure out the height of these 2 points. Remember, the height of the graph is just the output to the function. To figure out the value of my relative maximum, all I have to do is take that x value and plug it into the function. I just have to figure out what is f of negative 1. That's not that hard. Like, we've been doing that for a long time, figuring out y values that correspond with x values. But it gets a lot more complicated when we've already taken numbers and plugged them into the second derivative, or if you're using the first derivative test, you've plugged them into the first derivative. it can get hard to remember what each of the different functions represent because there's really three functions going on here, right? There's the function, and then the first derivative of that function, which is itself a function, and then the derivative of that first derivative, which is the second derivative of the function, which is itself also a function. But it's not the first or second derivative that I want to plug -1 into, it's the function itself. Maybe some color coordination will help. To figure out the value of my relative maxima, I just have to evaluate f of -1, which is 2 times -1 cubed minus 9 times -1 squared minus 24 times -1 plus 5. Let's see, -1 cubed is -1, -1 times 2 is -2, -1 squared is +1, and +1 times -9 is -9. -24 times -1 is +24, and then I got +5. I got 29 on the positive side, and I got -11 on the negative side. -29 plus 11 is 18. The value of my relative maximum is 18. What about the value of my relative minimum? Exact same thing. Now we're just going to take 4 and plug it into this equation. F of 4 would be equal to 2 times 4 to the third power minus 9 times 4 squared minus 24 times 4 plus 5. This is going to be a little bit miserable without a calculator, but hopefully I can do it. Let's see, 4 cubed is 16 times 4, which is 64, and 64 times 2 is 128, I believe. 4 squared is 16, and 16 times 9, let's see, 16 times 10 is 160, but I got one less 16, so I guess I got 144, and that's going to be negative. 24 times 4, well, 25 times 4 is 100, but I'm 1 4 short of 100, so I guess I'm at 96, and that's also negative. And then I got this plus 5. On the positive side, I got 128 and 5 more, so I got 133. And on the negative side, I got -144 and -96, which is -240. 133 minus 240 is -107. When I put 4 into my function, -107 comes out. Therefore, the value of my relative minimum that happened at x equals 4 is -107, as we can kind of confirm when we look at the graph here. That appears to be the height that I see here. How about one more example, and then we'll call this video good. This function again, maybe it'll bring back bad memories. You saw this in the previous section. My function f of x equals 7 minus x squared minus x minus 5 times e to the negative x power. Let's first look for any relative minima or maxima. Collectively, they can be referred to as relative extrema. Well, first I got to figure out my critical values. And to figure out my critical values, I need to know the first derivative and specifically when it's equal to 0. So first let's figure out our first derivative. The derivative of this mess, the 7 goes away, turns into a 0. To figure out the derivative of this side, I got to use the product rule. The derivative of the first thing, the x squared minus x minus 5, is 2x minus 1. And then I leave the e to the negative x, the second thing, alone. And then I add to that the derivative of the second thing. The derivative of e to the negative x is negative e to the negative x power, using the chain rule here. And then I leave the first thing alone, the x squared minus x minus 5. And I got to be really careful with parentheses. I'm subtracting this entire thing from 0. As we saw in a previous video, both of these terms have an e to the negative x in them, and it makes life a little bit easier to factor out a negative e to the negative x. If I do that, what I'm left with here is 2x minus 1, because here's the negative and here's the e to the negative x. And if I do that over here, I can get rid of these outer parentheses by taking this negative and distributing it through. So that gives me negative this e to the negative x times this 2x minus 1. And then this negative and this negative make a positive e to the negative x that's multiplied by x squared minus x minus 5. I can now factor out an e to the negative x. If I do that, I'm left with this negative and this 2x minus 1. In other words, negative 2x plus 1. And if I do that over here, I'm left with x squared minus x minus 5. If I combine like terms, I got e to the negative x times x squared minus 3x minus 4. I get critical values if f prime of x is equal to 0. And now that I know what f prime of x is equal to, e to the negative x times x squared minus 3x minus 4, I can set that equal to 0 and solve. Something times something equals 0 if e to the negative x equals 0, or if x squared minus 3x minus 4 equals 0. There's no solutions over here. There's nothing I can raise e up to make it equal to 0, but there are solutions over here because this factors is x minus 4 times x plus 1. So I get solutions when x equals 4 or when x equals negative 1. My critical values happen when x equals 4 and when x equals negative 1. Now I need to classify those critical values as local maxima or local minima. I'm going to do that using my second derivative test. To use my second derivative test, I need to know the second derivative, f double prime of x. Maybe I'll do that over here. To figure out the second derivative, I need to take the derivative of the first derivative. I'll use this form of the first derivative to try to make the algebra as easy as possible. Got something times something, so I got to use the product rule again. The derivative of the first thing is negative e to the negative x. I leave the second thing, the x squared minus 3x minus 4, completely alone. The derivative of the second thing, the 2x minus 3, times the first thing, leaving that completely alone, e to the negative x. This time I'm going to factor out a negative e to the negative x from each of these two terms to keep my x squared term positive. If I do that from the first term, I'm left with x squared minus 3x minus 4. And if I do that from the second term, this e to the negative x comes out in front, and the sign changes on both of these because I'm pulling out a negative also. So I get minus 2x plus 3. My second derivative is negative e to the negative x times x squared minus 5x minus 1. Now that I know my second derivative, I can use the second derivative test to classify these two critical values as either local minima or local maxima. Let's start with the critical value at 4. F double prime of 4 is equal to negative e to the negative 4th power times 4 squared minus 5 times 4 minus 1. Ooh, how am I ever going to figure out the value of that thing? Well, the good news is you don't need to. All you got to figure out is whether this is a positive number or a negative number. Negative e to the negative 4th power is a negative number. Why? Because it's the negative of 1 divided by e to the 4th power. And 1 divided by e to the 4th power is a positive number, so the negative of a positive number is a negative. What about this polynomial? Well, I got 16 minus 20 minus 1. What's that equal to? Well, it's easy enough to calculate. I think it's negative 5 in this case, but I don't really even care what it's equal to. I just care that it's a negative number. I got a negative times a negative, so I got a positive. What I'm saying is at 4, the second derivative is positive. What does that mean? It means my graph is concave up. The flat point in a concave up graph is a local minimum. Of course, we already knew that because we have this graph up here, and we can look for 4, and we can tell visually, if you have really good eyes, that that's a minimum and not a maximum. But with our new algebraic powers, we don't even need the graph to do that. What about classifying our other critical value? Well, we got to figure out the second derivative when x is equal to negative 1. Copying this equation, changing all the x's into negative 1s, I got negative e to the negative 1, in other words, positive 1, times negative 1 squared minus 5 times negative 1 minus 1. E to the first power is a positive number, and the negative of a positive number is a negative number. Negative 1 squared is 1, plus 5 gets me up to 6, minus 1 leaves me with 5. I don't care that it's 5, I just care that it's positive. A negative times a positive is a negative. What that means is my graph is concave down at x equals negative 1. What that means is negative 1 is a local maximum. Oh yeah, I remember that on the graph up here. At negative 1, I clearly have a local maximum. Before ending this video, I want to teach you one more vocabulary word. It's this idea of an absolute or global maximum. The idea with an absolute or global, there's two different adjectives that you can use, maximum, is it's the point that's higher than any other point on the graph. So this point right here is a relative maximum because the second derivative at negative 1 was a negative number, but it's also an absolute or global maximum because it's higher than any other point on the graph. To be a relative max, you just need to be kind of higher than all of your neighbors. To be an absolute max, you have to be higher than any point on the graph. But we can see just by looking at it that it's higher than any other point on the graph, so it's an absolute maximum. Contrast that with this point down here, which is definitely a relative minimum. We know it's a relative minimum because when we did the second derivative test at 4, we got a positive number coming out of the second derivative, so it's concave up, so it's a local minimum. but it's definitely not an absolute minimum. Why not? Because there's plenty of points, like down here, for example, that are lower than this point. There's no points higher than this point, so it's an absolute maximum, but there are points lower than this point, so it's not an absolute minimum. This critical value is an absolute max. This critical value is not an absolute minimum. That's a lot of information for one video, so I'm going to stop talking.